Alrighty, so at the beginning of the last chapter, we talked about the last section, we talked about colligative properties and how they depend on how the particles are dissolving in the solution, and that interferes with freezing or boiling or the vapor pressure. We talked about how it doesn't matter on what type of particle it is, but it does matter on how many. So if you have a lot of dissolving ions, they're going to interfere a lot more with the vapor pressure lowering, the freezing point depressing, and the boiling point elevating. If you have less, it's going to affect it less. So we know that colligative properties depend on the number of dissolved particles, and therefore electrolytes are treated slightly different than non-electrolytes when determining colligative properties. Now, why would you think that's the case? Why are electrolytes and non-electrolytes important when we think of colligative properties? What is an electrolyte and what is a non-electrolyte? Well, an electrolyte, especially a strong one, is something that completely dissolves in solution. So if we have sodium chloride in solution, it becomes sodium and chlorine. So I go from 1 mole of a substance to 2 moles of ions. If I think of a non-electrolyte, let's say glucose, I'm going to dissolve it as glucose. It does not split up. So you have 1 mole and 1 mole dissolved. Therefore, the glucose is going to affect the colligative properties different since it's a non-electrolyte. So let's think of the freezing point depression of a 0.10 molal, so for molality, sucrose, is 0.186 degrees Celsius. But for sodium, it's twice that amount. Now that's again because sodium chloride splits up into 2 moles of ions, whereas sucrose, since it's nonpolar and a non-electrolyte, will be 1 mole, affecting it less and depressing the freezing point less than that of a ionic substance, a strong electrolyte. So the ratio of moles of particles in solution to moles of formula units dissolved is called the Van Hoff factor. So then it changes a little bit the way of how we think of colligative properties. So a great way to think of this is ion pairing first to get a little bit more of an idea how these things change. So since 1 mole of sodium chloride produces 2 moles of particles in solution, we expect the Van Hoff factor to be exactly 2, right? We know that NaCl becomes Na plus Cl. All right, so immediately I say that when I have this, I have 2 moles of ions. Or even, let's say you have calcium chloride. Now, how many moles of ions of calcium chloride would you produce? Well, I have calcium ion and chlorine ion. However, you have 2, right? So that's 3 moles. Now, that's what we expect. However, in reality, it's a little bit different because of something called ion pairing. So this expected factor only occurs in very dilute solutions. So the Van Hoff factor, we would think, is 2. But in actuality, for a 0.10 molar sodium chloride solution, it's 1.87, which is a little bit less than 2. And for a 0.01 molar solution, it's 1.94. So when we have 0.1 sodium chloride, the Van Hoff factor is 1.87, so more concentrated. When we have an even more dilute solution, because you have less salt, it is 1.94. The Van Hoff factor approaches the expected value at infinite dilution, so as the concentration appears 0. There's always a table of the measured and the expected Van Hoff factors for different electrolyte solutions. The reason that the Van Hoff factors do not exactly equal expected values is that some ions effectively pair in solution. So we expect the dissociation of an ionic compound to be complete in solution. In reality, however, the dissociation is not always complete. At any moment, some of the cations will pair with the anions. So sometimes what we see is that some of the sodium and the chlorine will pair together, so therefore they're no longer separate ions, but they're sodium chloride. So because sometimes the hydrated anions and cations get close enough together to actually pair, it lowers the concentration because of them not being individual ions anymore. So all of our colligative properties are affected by the different Van Hoff factors. So before we get into the osmotic pressure, thinking of the vapor pressure of sodium chloride solution, it's lowered about twice as much as that of a non-electrolyte solution. So to calculate the vapor pressure of a solution containing an ionic solid, or the freezing point depression or boiling point elevation, we have to take into account that amount of ions. So our colligative properties now change to the Van Hoff factor times the molality times freezing point depression. For our boiling point elevation, the Van Hoff factor times molality times boiling point elevation. For our osmotic pressure, it is our Van Hoff factor times the molarity, the R constant, and the temperature. So just as freezing point depression of a solution containing an electrolyte solute is greater than of a solution containing the same concentration of a non-electrolyte, the vapor pressure lowering is greater for the same reasons. So the vapor pressure of sodium chloride is lowered about twice as much as it is for non-electrolyte, because non-electrolyte doesn't dissolve, sodium chloride does. So to calculate the vapor pressure of a solution containing an ionic solute, we need to account for the dissociation of the solute when we calculate the mole fraction. The way that you do this is when you, for the vapor pressure, calculate the mole fraction of a substance, you take the moles of substance over moles total times the moles of dissociation. So that's how our vapor pressure changes. You account the ions dissolved in the vapor pressure through the mole fraction by dividing through the mole total, but making sure you multiply how much the solute is dissolved in. Now, thinking a little bit more to real life situations. So doctors and other healthcare professionals often administer solutions to patients. So the osmotic pressure of these solutions is controlled for the desired effect of the patient. Solutions having osmotic pressure greater than those of the body fluids are called hyperosmotic. These solutions take water out of the cells and tissues. So when a human cell is placed in a hyperosmotic solution, it tends to shrivel as it loses water to the surrounding solution. Solutions have osmotic pressure less than that of the body are called hyperosmotic, hypo. These solutions pump water into the cells so they look a little bit more swollen. And then lastly, we have intravenous solutions, which are IVs. Those that are administered directly into the patient's veins, must have an osmotic pressure that's equal to the body fluids. So these solutions are called isoosmotic or isotonic. When a patient is given an IV in a hospital, the majority of the fluid is usually in an isoosmotic, isotonic saline solution, a solution containing 0.9 grams of sodium chloride per 100 milliliters of solution. In medicine and in other health-related fields, solution concentrations are often reported in units that indicate mass of the solute per given volume. So usually what we've learned is in percent by volume units that we've seen already. So basically, when you're getting medical attention, the osmotic pressure that you're given of a solution has to be equal to or helping you in the situation that you need. So a 1.2 mole aqueous solution of ionic compound with the formula of mx to the second has a boiling point of 101.4 degrees Celsius. Calculate the Van Hoff factors of mx at this concentration. So because there's a lot of new information today, I want us to save this problem for next week. So I want you to try this on your own. We're going to go over it next lecture. It's not going to be due. This is not an engagement problem, but I want you to attempt this, and then I'll ask you about it next week so we can go over it together. Last little bit of this chapter is colloids. So now we're just moving on to a little bit more theoretical stuff. So we talked about solutions, specifically aqueous solutions, where you don't really see the fact that there's salt in water. Now think about if you have like fog, smoke, whipped cream, or really soapy water. Now, those are also solutions because things dissolved, but it's more easily seen through the eye. Now, that's something called a colloid or a colloidal dispersion. It is a mixture in which a dispersed substance is finally divided into dispersing medium. Whether or not a mixture is a colloid is determined by the size of the particles it contains. Now, again, a colloid, the particles have to be bigger because we actually see the solution. We see that it's different. It doesn't just look like a clear solution. So if the particles are small, then the mixture is a solution. And if the particles have a diameter that's greater than 1 micrometer, like sand, so when we have sandy water, we actually see the sand in the water, the mixture is a heterogeneous mixture, a colloid. If the particles are between 1 nanometer and 1,000 nanometers, we have a colloid. So again, if we have, I should rephrase this, if we have greater than 1 micrometer, we have a heterogeneous. If we're then in between 1 nanometer and 1,000 nanometers, that's when we have a colloid. So colloidal particles are small enough that they stay dispersed throughout the dispersing medium by collisions with other molecules or atoms. When you view a colloidal particle dispersed in a liquid under a microscope, you can witness its jittery motion. So you can see the random path that these take. That's called the Brownian motion. It's caused by a colloid with molecules in the liquid. So soap forms a colloid because of its unique structure. One end of the molecule is ionic and therefore interacts strongly with water molecules via an ion dipole. The other end of soap molecule is a long hydrocarbon tail. So soap looks something like this. You have a bunch of hydrocarbon, like a long hydrocarbon tail. And then you have a polar end. So the ionic head, so we have sodium here involved, I should say, because this is carbon and these are my two oxygens. And the nonpolar tail gives soap its unique kind of structure. So when enough soap is then added to water, the soap molecules aggregate the structure called micelles. So in a micelle, the nonpolar tail of soap molecules or of other molecules that have properties that are similar to soap are oriented inward. So when they interact with one another. So think that they're kind of forming like from the long line into like a ball. And the ionic heads are oriented outward, where they can interact with polar molecules. So that all the nonpolars are going kind of into a ball, and all of the surface that's exposed is the ionic head, which is then what reacts with polar water. The micelle structures are responsible for the haze seen in soapy water. They are too small to be seen by the naked eye, but they still scatter. So we can visualize the scattering of those molecules, the fact that they're turning and that the different types of reactions are out, is through something called the Tyndall effect. We can scatter light and visualize the actual aggregation of the soap. Again, we have these long molecules and they are vibrating, where the non-carbon tail is kind of going into a circle and the polar part of it is out, which is actually what reacts with water, which is why they mix. But because they're so big, that's how we see them as soap, very hazy. And visualizing that through light is called the Tyndall effect. And that's all we have for this chapter. So review this, go over the different videos, do those engagement questions, start working